All right, so this is actually still section 8.1. There's a lot of material in 8.1, and there's actually some material that I think should be in 8.1 that's not. So this is going to be even longer than it needs to be. Sorry. So chapter or section 8.1 actually starts talking to you about types of reactions. So one type of reaction is a combination reaction. So this is a reaction in which typically we have two or more reactants combining to form one product. But in more general terms, a combination reaction always has more reactant species than product species. So the number of reactants, so if we have X plus Y plus Z reacting to form A plus B, we've got 3 reactants and 2 products, so 3 reactant species and 2 product species. So I note that instead of talking about the individual molecules, but the species themselves, there's 3 on the left and 2 on the right. That's still a combination reaction. But that's not what we typically call a combination reaction. Typically, it's forming one product, but I want you guys to know that there are more general ways to talk about combination reactions as well. But this is an example of a combination reaction that you're actually probably a little familiar with, is the reaction of hydrogen gas and oxygen gas to form water vapor. So this is how we make water, actually. And there's a fun little video that goes along with this, if I can, maybe it's not a video. Oh, here we go. Cool, right? So that is a hydrogen balloon. So it's a balloon filled with hydrogen gas, which is why it floats, because hydrogen has a lower density than oxygen. So it's a hydrogen balloon. And when we set it on fire, then the hydrogen escapes from the balloon and reacts with the oxygen in the air and forms water vapor. We don't really see the steam in the midst of all the fire, but it's forming water vapor. There's steam involved, and it's also a very loud explosion. This is one demonstration that we love to do in chemistry, and I'm sorry you guys didn't get to see it. But if you go to any like Halloween demonstrations or something in the future, I'm sure they'll have this. This is the hydrogen balloon demo. It's a lot of fun. So I can also look up a video of Dr. Collins doing it if you're interested in that. This one is just a random person from the internet, but we do have a recording of Dr. Collins doing it. So we have a hydrogen gas balloon, reacts with oxygen in the air when we light it on fire. So this is actually a combustion reaction because we are reacting with oxygen. So this is the combustion of hydrogen gas to form water. So here we're talking about combustion as well as a combination reaction. So this is generally just called a combination reaction because we have 2 reactants and 1 product, but it's also a combustion reaction technically. All right, here's another combination reaction. We take zinc powder and solid iodine. So the zinc powder is a white powder, I believe, and we react it with iodine powder, which is this darker powder down here. We just mix them together. You literally just mix the solids, and we end up with zinc iodide, which is a solid. But the reaction heats up when we mix them together as well, and that changes any excess iodine into gaseous iodine from the heat evolved through the reaction. It heats up the iodine enough that it becomes a gas. So this reaction is pretty cool because we're mixing 2 solids together, which doesn't sound very exciting. It's like mixing M&Ms and Skittles. You wouldn't think anything would happen, but these 2 solids are reactive, so they react to form zinc iodide, And if we add enough extra iodine, this reaction that's happening, that's heating up when it's forming zinc iodide, it's heating up, and if we add extra iodine, that excess iodine is going to be heated up as well, and it's going to heat up enough that it sublimes and turns into gaseous iodide, which is purple, which is pretty exciting. So this is a combination reaction again. We have 1, 2 reactants forming one product. Combination. We go from more reactants to less products. All right, and the opposite of that, basically, the opposite of that basically is a decomposition reaction. We have typically a single reactant decomposing into 2 or more products. So this time we're going the opposite way. In more general terms, a decomposition reaction always has fewer reactant species than product species. So this would be like X plus Y going to A plus B plus C. So typically it's just one reactant decomposing into 2 or more products, but I want you guys again to know that there are more general versions where we can have 2 reactants turning into 3 products or more, as long as we have fewer reactant species than we end up with as product species. So we are making more things than we started with. And like I said, a decomposition reaction is basically the reverse of a combination reaction and requires additional energy. So for example, water, we saw the reaction of hydrogen gas and oxygen gas to form water in our balloon. But this is a different example where we're going from liquid water to gaseous, or to hydrogen gas and oxygen gas. As you know, water is very stable under normal conditions, but you can make it decompose into hydrogen gas and oxygen gas if we use electrical energy. And this is a process called electrolysis. So often this is something that you might see. This is a way to purify water. This is also used in different electric vehicles. We use electrolysis to form gases that help power different processes. So this process called electrolysis requires electrical energy. So I'll put an energy over my reaction arrow. So we take water, we put in some electrical energy, like we shoot in some volts of electricity to our water, and that electrolysis results in hydrogen gas and oxygen gas, which is the opposite of the reaction we saw with our hydrogen balloon. This is decomposition of water instead of the combination to form water. All right, let's take a look at a few reactions and see if we can identify what kind they are. This image shows the reaction of mercury oxide reacting to form mercury metal and oxygen gas. So we've got some solid mercury oxide in this test tube, and we're heating it up over a Bunsen burner. And it is reacting to form mercury metal, so liquid mercury, note the liquid physical state, and oxygen gas. So what type of reaction is this? We have mercury oxide, 1 reactant, and we have mercury metal and oxygen gas, 2 products. So 1 reactant, 2 products. This is a decomposition reaction. We have less reactants than we have products. All right, what about this one? So this one is not pictured, but lithium metal and nitrogen gas can react in a rare reaction where something burns without the presence of oxygen. So this is basically like a combustion reaction, except using nitrogen gas instead of oxygen gas. So this is a really rare reaction where something is burning without oxygen. So we can burn lithium metal using nitrogen gas, and a flame, a starter of some kind. So we're burning in the presence of nitrogen instead of oxygen, which is pretty cool. Anyway, so we've got lithium metal, note that it's a solid, and nitrogen gas, and we're forming lithium nitride, which is also a solid. So we're taking one reactant, two reactants, and forming one product. What type of reaction is this? Got more reactants than products this time. So this is a combination reaction. Decomp for the first one, combo for the last one. So we're taking two things and putting them together, so that's a combination reaction. All right, so there are also other types of reactions. So we talked about we talked about combination reactions, we talked about decomposition reactions, and we talked about combustion reactions a little bit. So combustion reactions, let me emphasize something here for you with a combustion reaction. Combustion reactions, so any combustion reaction that occurs with a organic molecule containing carbon and hydrogen and oxygen. So it doesn't have to have oxygen, it could just be a hydrocarbon, but any organic molecule with carbon and hydrogen, if it is a combustion reaction, is always going to produce carbon dioxide and water. Those are always the products of this combustion reaction. So any combustion reaction with a hydrocarbon or other organic molecule, usually composed of CH and O, is going to result in carbon dioxide and water. So that's all that your book wanted to emphasize about combustion reactions. So I wanted to go back to that and show you as well. Anyway, last type of reaction that we're going to talk about, which your book does not mention, are displacement reactions. So sometimes we call them replacement reactions. I am always going to call it a displacement reaction, so I apologize if your book calls it a replacement reaction, but just know it means the same thing. So replacement or displacement reactions are ones where the number of reactants is equal to the number of products. So we talked about combination and decomposition, where we change the number of reactants and products. Now we're talking about these displacement reactions, where one ion or one atom displaces another so that we have the same number of products as reactants. So displacement reactions, sometimes also called exchange reactions. One part of a compound displaces another. So let's see what that looks like. There's single displacement reactions and double displacement reactions. We're going to talk a lot more about this one in chapter 9, where I believe they actually call it a single displacement reaction, or a hydrogen replacement reaction is one type, but I don't know that they ever actually mentioned the term double displacement again in your book, so I wanted to talk about it now because several types of reactions that we cover in chapter 9 are double displacement reactions. They can be categorized as double displacement reactions, and that's the term you might hear in the lab, so I wanted to make you aware of it now. Another thing you might hear in the lab is metathesis reactions. Double displacement reactions are also called metathesis reactions. So there's lots of different terms here. Replacement, displacement, exchange reactions, metathesis reactions. These all mean the same thing, that we are displacing one part of a compound with another. So single displacement means that we have two things together and one thing by itself. And when we react, we mix it up. So say we have something with A and B, and then we react it with C, we end up with A by itself and BC. So for example, This is one of the first reactions I showed you today, the reaction of HCl and magnesium metal. In this reaction, we have H and Cl together. There are A and B, and we have magnesium. And when we react them, we form hydrogen gas. So hydrogen by itself, so we split up that A, and then we put the Cl with Mg. So we put B and C together, MgCl2. That is a single displacement reaction. We displaced the hydrogen with our magnesium. So the magnesium popped in where the hydrogen was, and hydrogen had to split off and go by itself so that magnesium could combine with the chloride. Double displacement is a little more obvious. Double displacement is like this one, like NaCl, AgNO3. That was the very first one I showed you today with the white precipitate, and I can't get a G to form here. Here we go. So silver nitrate and sodium chloride, we formed silver chloride. That was our white precipitate. And the other product was sodium nitrate, which we didn't actually see because it was still dissolved in the water. So it doesn't matter how you think about it. You can think that the silver displaced the sodium and the sodium displaced the silver. So they swapped places, they swapped partners. Silver ended up with chlorine and sodium ended up with nitrate. They swapped their partners. That's a double displacement reaction. And I use this like color coding scheme to try and help you remember that. Alrighty. Now moving on to section 8.2. This is all about combustion reactions. This is something called combustion analysis. So in more general terms, there are several types of analysis that are done in chemical laboratories, and those are usually to, 1, determine the chemical formula of an unknown compound, 2, determine the composition of a mixture of compounds, or 3, to determine the purity of a chemical sample. We're going to focus on this first one, although these others are all very important. In combustion analysis, we have a sample that is weighed, and then we burn it in the presence of excess oxygen. So basically we just burn it in natural air, and it gets as much oxygen as it wants from the atmosphere. This converts all of the carbon to carbon dioxide and all of the hydrogen to water. So all of the carbon that came from our sample ends up as carbon dioxide. All of the hydrogen that came from our sample ends up in water. So we can find the amount of carbon and hydrogen from the original sample and the ratio of those two elements to each other from our original sample based on the amount of carbon dioxide and water produced in the combustion reaction. So the data produced from a combustion analysis can be used to determine the empirical formula of a hydrocarbon with the form CXHY. Combustion analysis can also be performed on compounds containing carbon, hydrogen, and oxygen. In this case, we have to do the first part with carbon and hydrogen first, and then we have to use the amounts of carbon and hydrogen from our original sample and the mass of our original sample to determine how much oxygen was in the original sample, because we can't get it directly from the combustion data because one of our reactants was also oxygen gas, not just the combustion, or not just the hydrocarbon or the organic molecule that we started with. So I'm going to go over this example instead of the normal like CXHY version. I'm not going to go over that one. I'm going to go over this version because this one's harder. So I'm going to do the harder one first. All right, so we have a 7.343 gram sample of an organic compound containing C, H, and O. We burn it, and what comes out? We get 12.23 grams of carbon dioxide and 4.006 grams of water. So we have these little traps, little areas in our combustion analysis apparatus that traps carbon dioxide and separates it from a separate trap of water so that we can get the mass of carbon dioxide by itself, the mass of water by itself. So we did our combustion analysis, and this is what we got. 12.23 grams of carbon dioxide, 4.006 grams of water. And that's going to tell us how much carbon and hydrogen we started with. Cool. And then in a separate experiment, the molar mass of the original sample, our organic molecule, was 132.1 grams per mole. And we're going to use that for the molecular formula. But let's start with the empirical formula. All right, so so we've got 12.23 grams of carbon dioxide. All of our carbon came from this carbon dioxide. So if you use the periodic table that we give you on the quizzes and the exams, I added up the molar masses of carbon and oxygen atoms to find that the mass of carbon dioxide, the molar mass of carbon dioxide from that periodic table, is 44.098 grams per mole of carbon dioxide. So now we convert it to moles of carbon dioxide. Now we want to go to carbon. So moles of carbon dioxide. So in every 1 mole of carbon dioxide, we have 1 mole of carbon. There is 1 molecule or 1 atom of carbon in 1 molecule of carbon dioxide. So 1 mole in 1 mole. Okay, and then last I want to get the mass of carbon. So in 1 mole of carbon, we've got 12.011 grams. All right, and if we multiply across the top, divide the stuff on the bottom, I found that we have 3.3378 grams of carbon. Okay, so I'm going to write that up here, 3.3378 grams carbon. Now I'm going to erase and do the same thing for hydrogen. So that is the mass of the original sample that was composed of carbon. So the carbon atoms in our original sample weighed 3.3378 grams. All right, now hydrogen. 4.006 grams of water. And if I use that periodic table again, I find 18.0152 grams per mole of water. All right, now we want to go to hydrogen. So unlike carbon dioxide, it's not 1-to-1. There are 2 moles of hydrogen atoms in 1 mole of water molecules. So there's 2 hydrogen atoms in 1 molecule of water. So that is important that we keep that ratio in mind and don't just assume that it's 1-to-1 like we did with carbon dioxide. It's not the same. Okay, and then lastly, we multiply by the molecular weight, the molar mass of hydrogen atoms, which is 1.0079 grams per mole from that periodic table. And that gives me 0.44825 grams of hydrogen. Okay, so I'm going to put that here, 0.44825 grams hydrogen. And I'm going to erase again. All right, so our original sample that we weighed before we reacted it with oxygen, before we put it through our combustion analysis, that original sample weighed 7.343 grams. I'm going to call that CHO. That 7.343 grams is composed of 33 or 3.3378 grams of carbon and 0.44825 grams of hydrogen. So if we get rid of the carbons, we get rid of the hydrogens, all we're going to have left is the mass of the oxygen from our original sample. That's exactly what we want. So when we do that, I end up with 3.55695 grams of oxygen. Put that up here. 3.55695 grams oxygen. So that's oxygen atoms, because our original sample did not contain oxygen gas, it contained oxygen atoms. Okay. All right, so we're almost done, I promise. All right, so we take that mass. So let's start with carbon. 3.3378 grams of carbon. And now we want to find moles. 12.011 grams per mole of carbon gives us 0.277895. I'm using a lot of extra sig figs because I don't want to round till the end. It's very important not to round till the end. So that's our moles of carbon. Let's do hydrogen. 0.44825 grams of hydrogen. Divide by our molar mass of hydrogen, 0.0079 grams per mole. And that is 0.444737 moles of hydrogen. Okay, I'm just going to erase over here so that I can rewrite my oxygen. So lastly, we have our oxygen, which was 3.55695 grams of oxygen, and that's 15.9994 grams per mole. So we end up with 0.222318 moles of oxygen. All right, so this one's the smallest, so we're going to divide everything by that number. So this divided by 0.222318, and this divided by 0.222318 gives us 1 mole of oxygen, because this divided by itself is 1. 1 mole of oxygen, 1.25 moles of carbon, and 2 moles of hydrogen. Okay, we're almost done. I know I said that already, but this time we're really almost done. So we've got our mole ratios. Now we can write our empirical formula. So we want these to all be whole numbers. This one's not a whole number, so it's 1 1/4. So if it's a quarter, we need to multiply by 4. So we need to multiply them all by 4. So we're going to get 5 carbons 8 hydrogens and 4 oxygens. So our empirical formula is C5H8O4. So whatever our organic compound was that we started with, using combustion analysis, we were able to find out the empirical formula of that compound. And if we use this molar mass and compare it to the empirical formula mass, we'll find out that this is actually the molecular formula as well. So you guys can do that at home and test it. So 5 atoms of carbon times 12.011 grams per atom, or per mole, I guess, plus 8 times 1.0079 grams per mole, and 4 times 15.9994 grams per mole, all added together, gives us 132. So if the molar mass is equal to the empirical formula mass, then the empirical formula and molecular formula are the same, and we're done. So this is for you guys. These are steps in determining these formulas. If you are only doing hydrocarbons, so hydrocarbons, I mean this CXHY. If you're only doing hydrocarbons, you don't need to do step number 3. Step number 3 is what I did to get the mass of oxygen in our organic compound. That was a CHO. If you don't have oxygen, you can skip right to step 4. These are the steps that I followed, and this is the steps that you should follow. I would not memorize these steps, just know how to use them. And one more type that your book doesn't actually cover, but this is also very related, is determining the empirical formula of binary compounds using their masses that are combined together. So we combine 15.97 grams of chromium with excess bromine. We heat it up and mix it all together, and that forms metal bromide. So it's a chromium bromide. CRX, BRY is our formula. And we want to determine the empirical formula using the mass of chromium we started with and the mass of this metal bromide that we ended up with. So this one's easier actually than combustion analysis. Do 89.61 grams minus 15.97 grams. That tells you that you had 73.94 grams from the bromide and 15.97 grams, like you started with, from the chromium. Use the molar masses of chromium and bromine to determine the number of moles of each, and you should end up with CrBr3. So if you want, we can talk about that in class, but you guys should be able to figure it out from here. So we've got masses. You need to look up the molar masses of these elements on the periodic table and then convert to moles. And then you want to use the lowest number as your number that you divide by. So you actually end up with chromium being your lowest number. So you end up with 0.30714 moles of chromium and 0.92161 moles of bromine. So if you divide both of them by the moles of chromium, this is a 1 and this is a 3. So let me know if you have questions on that. This is the steps for doing that. So that's it for today, and I'll see you tomorrow.